Good morning and good afternoon, everyone. Welcome to our first ASEAN-Korea Water Treatment Working Group seminar. Let me introduce myself. My name is 제1차, a professor in civil and environmental engineering at Hanyang University, Korea. I'm serving as one of the leaders of the ASEAN-Korea Water Treatment Working Group, which is a multinational expert group established by the National Academy of Engineering of Korea and the Asian Academy of Engineering and Technology. Today, we are very excited to kick off the working group's first official event. Among the 20 members of the working group, we have invited 4 leading experts from Korea, Singapore, and Thailand. They will share their knowledge and insights and water and energy technology and discuss the challenges and opportunities in their countries. Each speaker is given 20 minutes of speech and 5 minutes of Q&A. While listening to each talk, please feel free to leave your comments and questions in the chat window. I will choose and read the questions after each presentation. So now let me introduce the first speaker from Korea. First speaker is Professor Yoon-jae Kim. He's a professor in Department of Mechanical Engineering at Seongkyungan University. He will be presenting on the topic of prospects for small hydropower development to support carbon neutrality policy. Now, please welcome Professor Kim.
So can you see everybody?
Yes.
Yes.
All right. Hello, everyone. So first, I'd like to thank ASEAN and the National Academy of Engineering of Korea and the officials for preparing the first ASEAN-Korea the Water Treatment Working Group seminar. I'm Professor YJ Kim, so Seongkyungan University. What I bring today is about the efficient use of the energy, so which is the task facing many Asian countries, including Korea too. As part of the carbon neutrality policies, it is how to efficiently utilize that hydropower wasted in the renewable energy sources. As far as I know, the Asian countries have that abundant hydro resources. As an alternative to realize the carbon neutrality policies, I'd like to analyze the prospects of the small hydropower generation as the climate change problems that becomes more serious and global efforts toward the carbon neutrality or the zero carbon policies being made. And I think the small hydropower is that our next potential to minimize and reduce the carbon dioxide. Against this background, I like to analyze the current status of the global hydropower generation and current status and problems of the hydropower generation in Korea, and then present the prospects and development direction for small hydropower generation. First, I'd like to talk about the carbon neutrality, the policy of each country, and starting with the definition and the necessity of the carbon neutrality. And then I'll talk about the renewable energy policies of each country. In particular, I'd like to outline the carbon emission right credits that may be of interest in most of the Asian countries. Third, I'll talk about the classification of the hydropower generation, the form of the hydro turbine, and then the optimal design techniques. How can we optimally design the hydro turbine cases? And then lastly, I'd like to end my presentation by addressing the development directions of the hydropower, especially the prospects of the hydroelectric power that based on hydro energy sources in our Asian countries. Okay, here is the carbon neutrality. As you know, that as activity to prevent an increase in the concentration of the carbon dioxide in the atmosphere. The carbon dioxide emissions are reduced as much as possible, and then absorption is the increase, the resulting of the net zero of these emission cases in here. That's the definition is there. So what is this kind of the carbon neutral policies and necessity? As you know, the Earth is the steep rise in temperature due to the fossil fuel use and then industrialization. You might be realized then from that Paris Agreement, 2015. So currently, the 1.5 Celsius degree of this that Earth's temperatures is so we should maintain or reduce these temperature rise cases in here. So if the global temperature rises by 2 Celsius degree, the possibility of the serious natural disasters, such as the heat waves and heavy snows, typhoon or hurricanes, rising sea levels, and decreasing use of the water increases in here. So efforts are required to suppress it to 1.5 Celsius degree, lower than the current temperature. So fortunately, governmental panel on climate changes, so-called IPCC, approved that a special report on global warming, 1.5 Celsius degree in 2018. So right-hand side, you might be sure that currently 1.5 is the Celsius degree that the coral reefs is going to be the decline, the 70 to 90% cases. But if this temperatures increase 0.5 degree to 2 Celsius degree cases, then almost 99% going to be declined. That's that climate change effects in here. So the global policy is going to be set up on this the carbon neutrality policies. As you know, that 1988, the Intergovernmental Panel on Climate Change is established. IPCC is established. And then 1992, that Rio Summit is held in the category of the UN framework, the Convention on Climate Changes. And then first, the Conference of the Parties is that held in Berlin in 1995. And then 97, we adopted the Kyoto Protocols. And then currently, year 2017, the COP23, they increased the ambitions to reach 1.5 the Celsius degree of the goal in here. Okay? That's the global policies in here. But what happened that each developed countries, that the national policies in here. As you can see that USA, United States, they rejoined the Paris Agreement after Biden administration is launched in here. And then greenhouse gas reduction target to be achieved by 2030 is set to the 50 to 52% compared to year 2005. And then eventually they aim to achieve the carbon neutrality by the 2050. What about the Germany? Germany also set up the year 2016, so-called the climate protection plan is 2050. And then year 2019, they set up the federal the climate protection act in here. And then eventually they announced that they plan to gradually reduce the greenhouse gas emissions, the 85% by year 2050. What about China? As you know, China is the world's largest carbon emitters. That's the year 2021. And they announced the pre-2030 carbon allocation and peak action plan and white paper on climate change response policy and actions in 2021. What of Japan? Japan also set up the global warming countermeasure state force, decide on the national, determine the contribution with the goal of reducing the greenhouse gas emissions to 26% by year 2030 cases. Okay. So all of that in the South Korea, yeah. Then also my country also established the law and institutional basis for promoting the carbon neutrality by enacting the framework act on the carbon neutral green goals to respond to climate crisis in 2021. And this government, and recently in March 2023, the first national carbon neutral green growth basic plans was announced to achieve the year 2050 carbon neutrality and realized green growth there. Okay? So every single country is concerned of this kind of the climate changes. Then what's going on? How can we reduce that carbon dioxide emissions? They must be set up that substitute the fossil fuel to renewable energy in there. And they set up the supporting policies in there. Okay. So as you can see, the demands for renewable energy increasing to reduce the greenhouse gas emissions. But most of that energy source from the fossil fuels accounts for approximately the 83% of them. And then renewables only account for approximately the 12% cases. Okay. So global greenhouse gas emissions by sectors, the energy sector is occupied almost the 73%, and then agricultural, then land use using the 18.4% cases. Okay. So most of these that energy sectors that emitted lots of the carbon dioxide gases. What about the issues the global primary energy cases? And as you know that oil, coal, and natural gases, which is came from the fossil fuels, is occupied most of that global energies in here. And then only small portions, less than the 10% later, that's occupied by the renewable energy system. Okay? And also include the hydroelectricity cases. Okay. So then, if this kind of the renewable energy policy is going to set up by developed countries or underdeveloped countries, what happened there? What's the benefit for developing countries in here? Okay? So developing countries maybe get some benefit by the clean development mechanism, CDMs in here. The developed countries, the developing countries that certify some emission reduction, so-called the CERs to the developed countries. And they also got some investment in technology to the developing countries, which is the most of the Asian country cases. So developing countries, the overseas investment in eco-friendly technology, and then sustainable domestic technologies, the developed cases in there. And also the developed countries, so reduce the green gas, and greenhouse gases, sorry about that, and then a reduction cost is in here. That's a general mechanism of the clean development for win technology between developing countries and developed country cases in here. Okay. So the most of countries that offered the policy, first is the price support and tax and the financial and other things. So price supports include the renewable energy portfolio standard and feed-in tariffs and feed-in premiums and contract for different cases. We use the promoter entry of the investigation system. And also tax support cases, the tax reduction and exemption tax credit. For example, USA is given the investment tax credit and production tax credit to increase the number of the investigations. Then financially, did all low interest loans and then successful loan cases, and the investment incentives by reducing the future uncertainty cases. That's a lot of the policy relating to renewable energy sources in here. And then, for example, England, and they offered from the year 2000 and 2014, they offering the price support and tax support cases, and included the USA also the price and tax that support programs is established there. Then what of the Germany? Germany also got some that include the price and tax. They include the financial support for renewable energy programs, support for renewable energy investment cost loans from year 2009. That's why the Germany, they discarded the nuclear power plant, and most of their energy sources come from the renewable energy cases. What about France? France also got the same stars in there. FIP, then option systems, ITC, and renewable energy or levy exemption programs operated here. What about in Japan? Japan also, starting the year 2003, so the RPS cases, FIT, then option system, the reduction, and FI plans. And they also got the designation of the offshore wind power promotion zones. Okay? So most of these kind of the developed countries that establish that this kind of the support programs to enhance that renewable energy stuffs in there. Then what's going on for remain the small hydropowers in the world cases? Only about the 30% of the world hydropower potential is developed, and further research on hydro turbines must be established to increase the efficiency and performance. Here is that Eastern Asia cases. That's the installed capacity is the 45,000 cases in here, the megawatt cases. And then remaining potential is the 29,000 megawatt may be used for the Eastern Asia countries, included as Central Russia, then the South Americas. They got the still lots of the potential to use the hydropower in here. Okay? So that then how we got to this kind of the hydropower. So the lots of the energy is required to in countries with a high proportion of the manufacturing industries like South Korea and Germany. We need a lot of that energy power to operate in this kind of the manufacturing industries, which is relating the steel plant, steel manufacturing plant, the automobiles, the shipbuildings, the petrochemicals industries. They need a lot of that that energy is needed. So in the case of the proportion of the hydroelectric power generation, but unfortunately the topographical or geological and the industrial effects they exist in it. So here is the annual power generation. So gigawatt hour. In Germany, so there's 587,000 gigawatt hour. In South Korea also that 563,000 gigawatt hours. That's that the most developed manufacturing companies or industries exist in Germany and South Korea. Then what's going on for percentage of the hydropower generation? Let's take the Norway. In Norway, almost 93% came from the hydropower. Okay, what about the South Korea? Just the 1.1% of this that hydropower generation. Then what's going on for percentage of the renewable energy, total power generation, including that hydropower? So Norway is a 97.7, the South Korea is a 6.5, only for renewable energy is near. So Korean government to try to increase this portion is that 13 percentage of the year. Okay. So then how can we classify the hydropower? Let me hurry up. So as you know, the types of the hydropower is a sturdy hydropower in here. That's a typical the large dam in here. And then pump to storage the hydropower cases. That's that using the include pumps that carry water to a higher reservoir to meet the power or need cases. And then run-of-river hydropowers utilize the flowing rivers. This is the most of our Asian countries should be thinking about this kind of the run-of-river hydropower techniques with the powerful hydro turbine cases. And then tidal powers and wave powers in here. Okay? Then based on this kind of, then we might be classified. The large hydropower is that depends on facility capacity. There's 100,000 kilowatt cases. Medium size is that less than 100,000 kilowatt cases, and small hydropower, mini hydropower, micro pico. In Korean, we using this one is called just the small hydropower. Okay, there's that capacity cases. Then how can you classify the turbines? Hydro turbine is classified two different types. One for impulsive type, and the other case is the reactive type. Impulsive type is then composed of the Pelton type and turbo type and cross flow type. the most of the current, the hydro dams using the reactive types include the Francis, then propeller coupling, and tubular types. Okay. Then Francis turbine is usually the wide range of set, so till the 600 meter cases in here. Okay. It needed the guide vane, runners, and then the spiral casings, drip tube cases, and also coupling tubes. Is that used at high flow rate and relatively low head until the 70 the meter cases in here. And then Pelton type is that used the low flow rate, but it used the high head cases. In here, the head means that falling water heights. We say this one is a head in here. Okay. And then cross flow turbines. So recently, this one is the last of the using here to easy to maintain due to the simple structure cases. And then this one, so net head, and then the discharge rate cases. If we have the small height, sorry about that. If we have the small height, then we might be using the propeller type or coupling type. If we have the large head but the small discharge rate, we might be using the Pelton type or turbo type cases in here. So we can classify this one large head, medium head, and small head. Then depends on its head. If this one is greater than 50 meter cases, we call this one is a large head in here. Okay. So then how can we design this kind of the hydro turbine? So most of the runner designs, the structure in the soundings, then rotor assemblies, and generator stuff in here. It's very important that component technologies in here. Then how can we optimize this kind of the hydro turbine? So we set up this kind of flow rate and geological and geographical that factors. We specify the conditions, and then one-dimensional analysis. If this one-dimensional is satisfied, then we forwarding the three-dimensional analysis, include a fluid flow problem and structural problem too. If this one is okay, then we analysis on the primary parameters and generation of the data set using the typically the design of experiment. And then generate the data maybe using the neural networks. So we set up the hyperparameter, then hyperparameter tuning performance test, and then we set up approximation model in here. That's a neural network, the techniques in here. Recently, the popular on this kind of the design society, so-called the AI techniques in here. We predict the optimals and then the safety simulations, and then finally we optimize the efficient hydro turbine here. Okay. So I'd like to explain the current state of the power generation facility in Korea. So Korea is domestic power generation is a high proportion of the power generation using fossil fuel, including nuclear power cases. And also we got a pretty small hydropower plant capacity, and it's insignificant compared to total the facility capacity here. So 17% from the nuclear, and 18% came from the renewable energies here. This kind of the renewable energies, then 73% is came from the solar, wind, and other stuffs in here. And then from this one, 8.3 cases, we only got hydropowers in here, the 0.9% in here. That's a pretty small here. Okay. Then there are some drawbacks and geographical problem or topographical problems. The installation limited place to drops, the falling water height, and then flow existing. And also contribution to power generation. So compared to general hydroelectric and then the pumping power generations, and the amount of the power generation fluctuates according to precipitations. In these days, is the weather condition in Korea is so we got the serious problems like that, and also maintenance cost, and then there are some that interest related to the users' interest in water use, so intertwined, and then the legal problems is exist there. Okay? So here is the prospects and developments, the direction for hydropowers. Then hydropowers is that the nuclear power and the wind power, solar is by low carbon the power sources here. Okay, so the most of these cases, and this one is that low carbon cases. So we seriously thinking about the hydropower here, but large scale hydropowers, we got the environmental problems in here. But the small hydropower cases, we wasted for a lot of the river cases. The most of the water is that the wasted here. We should revitalizing this kind of the wasting water. That's why we need that small hydro turbine here. So here is the China cases here. For example, from year 1945, then the recent cases in China, due to the three gorges that hydraulic big dams, they got this kind of the hydropower generations here. In here that
Professor Kim?
yeah, I'm done. Okay,
Yes,
I'm
good.
almost done.
Thank you.
Okay, I'm gonna hurry up. Sorry about that. Okay, here's the hydropower generation.
Ria,
total.
off
Okay.
mo ko dito.
Oh, okay, sorry about that. And then I like to talk about the age profiles. Is that the most of the developed countries should repair the dam. So China is recently developed these types in here. So aging problem also one of the problems compared to developing countries in here. Well, I think almost done. I think this one is the modernization of the aging powers requires the lots of money. But small hydropower is that we might be saved money and to increase the energy source in it. I think this one is that end of talk of mine here, but I like to finally conclude by saying that the small hydro generation should be actively promoted as a means of meeting the carbon neutrality policy, and technical support such as the policy support and high efficiency hydro turbine development then should be provided. Well, this is end of my talk, and thanks for your listening. Okay.
Thank you very much, Professor Kim. It was very insightful speech. Especially, we appreciate your nice introduction of the big picture of energy. Thank you very much again. If you have any questions, you can raise your hand, or you can let me know. Then we can entertain the question. I saw one message by Dr. Sue I believe she's here. Dr. I, are you there? I saw her name. If she's briefly out, she said that, let me read what she wrote in the message window. Many thanks to Professor Kim for sharing very interesting topic on small hydropower development to support carbon neutrality policy, which gave us very informative messages. Since carbon neutrality will greatly slow down global warming and solve our energy crisis, with accompanying benefits to air quality, ecological recovery, and urban and rural landscape. I guess what she was trying to say was agreed with Professor Kim.
Thank you.
Okay, thank you. Is there any other question? Professor Kim, let me ask you one question. You briefly mentioned the drawbacks of the small hydropower. I guess there can be some concerns installing those power generators in stream. Are there any concerns which become more severe here in Korea or in other Asian countries?
Okay. Now, as you know, that Korea, so we got the lot of the geographical problems to install the big dam, large dam I'm talking about. Yeah. Then the large dams is that the influence is that the environment. So we got some that the last of the coughing patients is come out near the large dams in here, and then it dissolved and disrupted the environment. But maybe hydro, the small hydro, the power system is not fit to in Korea. That when I travel the Asian countries, and the Asian countries got the abundant the water resources, and they just flow out and throw it out in cases. They never use them. That's why if we develop the efficient that hydro turbines, we might be reuse that wasting the water cases, and then that waste water. So we generate that electricity, and then we can protect our the environment. Okay? That's why I introduced that the small hydropower is the best method, best way.
Okay. Thank you very much, Professor Kim Jae.
Okay.
Yes. Now let's move on to the next speaker. Our next speaker is Professor Yang Hui Ying. She's a professor in engineering product development at Singapore University of Technology and Design. She will be speaking on new generation low-dimensional nanomaterials for water treatment.
Thank you. Thank you, Prof. Park. Charmy, can you allow me to share the slides? Thank you.
Please share your slide.
Okay, thank you. All right. So good afternoon, everyone. My name is Hui Ying. I'm from Singapore University of Technology and Design. I'm very happy to share with all the experts from Korean and ASEAN on some of these technologies and then sort of new coming technologies in the water treatment field. As we all know, and then also as Professor Kim just shared, that a net zero emission, like smart city or like carbon neutral city, will be a very dream kind of condition for every country to pursue. To achieve the net zero emission, the energy used in water treatment need to be largely reduced. So in our research lab, we use low dimensional nanomaterial for water treatment and then resource recovery. And today I will introduce some of our new discoveries to all of you. So there are many different technologies for water treatment. So basically for desalination, we have membrane technology. And then within the membrane technology, we have reverse osmosis, electrodialysis, nanofiltration, and then other methods. And we also have thermal method to kind of evaporate the water vapor from seawater and then get the condensed seawater and then also the cooling down of this water vapor to generate fresh water. So within this field, we also have a different method and approach allow us to effectively kind of evaporate the fresh water from seawater. But again, because we need to have a large amount of heat over here, the energy consumption is also very high. Alternative approach for seawater desalination treatment is a very important field. And within this field, there are many new coming technologies. And then today I will introduce one of them to you, that is capacitive deionization. So my capacitive deionization, actually, the concept is very straightforward. You have two electrodes. One is cathode, the other one is anode. And then you have a sort of two electrode being connected to a very minimum level of power. And then with that, we can see that we can have a cathode carry the positive charge, and then we can have an anode carry the negative charge. And in salty water or seawater, there are negatively charged chloride ions and positive charged sodium ions. So those sodium ions will go to combine with the negative charged electrode. And then also the chloride will go to combine with the positive charged cathode. So within this structure, the ions will be separate and then absorbed to different electrodes. And then the total concentration for charged ions will be reduced. So you have your water desalinate. And we can see over here, there are different salty level of ion concentration. For example, from 100 ppm to 1000 ppm, from 1000 ppm to 10,000 ppm, and then from 10,000 ppm to 100,000 ppm. So from this different domain, we can see that for thermal method, it will be very suitable for the water with a concentration from 80,000 to 100,000 or above 100,000 ppm range. And then RO reverse osmosis membrane technology will be very suitable for the water from around 2,000 ppm to around 80,000 ppm. And then for EDR or IEX softening, and those methods will be very suitable for brackish water treatment, which will be from a few hundred sort of ppm to 1,000 ppm. And then the CDI or like other CDI related technology will be sort of within this range as well. So within this a few hundred to more than 1,000 to 2,000 ppm range, we can use a CDI or EDR to do the treatment. So among all these different electrode material that we can choose to make this desalination electrode, there are some governing rules. So we have done some dynamic modeling for CDI per size to figure out a few key parameters that you need to pay attention when you want to design an electrode. For example, high electrical conductivity, large surface area, favorable per size distribution, good wettability, sufficient ion diffusion pathways, and so on and so forth. So with this few criteria, we can actually choose the ideal materials for this electrode fabrication and also desalination. So with this technology, we actually can achieve a sort of better version of CDI to remove the sodium and chloride from salty water. And then within this design, we have actually further modified the whole device. We actually implement a membrane structure. This membrane structure is ion selective membrane. So we have anion exchange membrane and then cation exchange membrane on top of this electrode. Those exchange membrane will prevent the co-ion co-ion explosion condition, and that will enhance salt absorption capacity, improve energy efficiency, and have the better cycling performance. So we have our group of very promising membrane CDI electrode material, for example, graphene composite, metal organic framework composite, bio-waste composite, and so on and so forth. And we also have a hybrid asymmetric CDI structure. For this asymmetric CDI structure, the two electrodes, we won't use similar materials, or we won't use similar type of materials. So we will selectively choose, for example, like a carbon electrode to be paired together with membrane or machine or like other sort of metal oxide nanomaterials to pair them together. And then this hybrid asymmetric CDI system can have this interaction electrode for sodium and carbon material for chloride. For example, we have like list down here many different materials that we have tried. For example, machine, titanium carbide, and then also sodium manganese oxide, fusion blue analogs, and so on and so forth. So the advantage for this enhanced hybrid asymmetric CDI, including enhanced ion removal capacity, low cost, synergetic effect, and effective ion swapping. And those will be very beneficial when you design your electrode. We have also figured out a new group of new Faraday materials for this type of CDI hybrid electrode. For example, sodium interaction mechanism to reduce the co-ion explosion. And then we have identified the nasicon, which is sodium and then also a sodium-based sort of metal organic framework. and related structure. For example, NMO, NTP, NVP, and then iron phosphide, and so on and so forth. And those materials have been proved to improve this salt absorption capacity to be above more than 100 milligram per gram. So, and we have also designed a more revolutionized idea, which is called a desalination battery. So the process for this is we actually figure out when we desalinated the water, the seawater, remove the sodium and chloride from seawater, we actually store those sodium and chloride inside the electrode. And once we want to discharge those ions to the sort of concentrate brine water, we actually release this energy. And then this energy can be utilized to power small device, power small equipment, and so on and so forth. And in this way, we actually store the sodium and chloride and then doing the energy storage concurrently. That's why we call this whole structure desalination battery. So we have enabled enhanced ion selectivity, favorable towards seawater with high salinity and multi-ion composition, high degree of freedom in terms of forms and scalability, and so on and so forth. For the mechanism and design for desalination battery, we can see that we have different steps for that. The first step, we actually design different electrodes. For example, we have active carbon, and then we have fusion blue analog. And then we have in the beginning, this is a kind of charging process. In this charging process, these chloride ions has been sort of absorbed by active carbon, and the sodium ion has been absorbed by this fusion blue analog. After we keep charging the device, and we can see that within one sort of designed or like period, those ions will be saturated into the sort of electrode. And after that, we will change the step to step 2, and that will be our discharge process. So in this discharge process, that we release the sodium and chloride back to the brine water. And then we go to step 3, and then we keep releasing those ions out. And in that way, we also power some small device and small sort of equipment. And then after that, until we go for the all neutral stage. So the AC and fusion blue analog both have been sort of released fully the sodium and then chloride ions stay host in their structure. And then this whole structure, we go back to stage 0, and the whole process start again. So the minimum energy consumption for this structure will be very low. So in fact, we can treat the seawater in a way that have this 0.127 watt-hour program. And then the energy consumption recovery rate can all be controlled by the applied voltage for the structure. So we actually also designed the sodium and chloride interaction sort of intercalation electrode by NMO and then lithium oxide chloride. And both structures have demonstrated the intercalation behavior for sodium and also chloride. So our big vision for this project is turning the ocean into a mega battery. So the desalination battery can be utilized as national taps and switch. So this battery can be engaged in specific reactions with salt ions. Seawater function as electrolyte, and desalination can be analogously treated as charging a battery to store sodium and chloride ions. And then this sustainable and low-cost solution that will be benefit many countries and meet the demand of water and energy concurrently. So we have also been working on lithium extraction method through this fluidic electrochemical system. So within the system, we can see that we actually design like a sort of our 3-step system. So we design a sort of water tank, and after that we have the selective absorption, step 1, and then we have this sort of water react with sort of electrons to generate oxygen, and then 4 sort of proton. And then this lithium will react with lithium manganese oxide to generate lithium manganese 2 and oxide 4. So after that, we will have the releasing cycle. So we have oxygen and then water and lithium and electron to react together to generate a sort of lithium hydroxide, and that will be our final product. And then this lithium manganese oxide will go back to the original stage. So by this, we can actually sort of recycle the very valuable resource from seawater. In this case, is lithium. So we can see that the seawater actually have lithium, sodium, potassium, magnesium, and then calcium. So we actually can see from these figures that different ions towards this manganese oxide have different free energy. And then from all this free energy, that lithium have highest free energy. That means when lithium being inserted into the complex, the largest amount of free energy will be released. And that means that lithium will be very stable after inserted into the complex and combined with the structure. And that is one of the particular reasons that the structure have the selectivity towards lithium. And that will be the important feature for the structure. And then also, we have also realized lowest lithium concentration sort of tested among all similar device or similar equipment, which is 7 ppm. And then the lithium extraction capacity for seawater condition can be as high as 20.6 milligram per gram in a very short time for 45 minutes. So this is a working prototype we have in our lab. And these are the different electrode material that can be utilized in this lithium recovery process. And then we also have done other monovalent cation removal through this geomembrane structure. For example, we have actually sort of treated different ions like potassium and then also sodium. And we can see that the different structure will have different selectivity towards potassium and sodium. And then we also have the selectively removal of boron to this nitrogen-doped graphene oxide. So this nitrogen-doped graphene oxide, you can see over here, have positive charge across the whole structure. And then this boron actually exists in water or any kind of water in the format of boric acid. So this is the boron metal ions in the middle. And then we have 4 OH groups at the 4 corners, and the whole structure will be in negative charge. So the negative charge and positive charge will attract each other, and then when they attract each other, there will be one water reduced from the whole structure, and the boron will be attached to this nitrogen-doped graphene oxide. So this boron will be permanently or chemically bonded to the structure, and the boron can be removed. As we all know that boron removal is a very challenging topic for most of the membrane technology, and with our design, we don't need to use any sort of very electricity intensive membrane technology. We can use this absorption technology through this nitrogen-doped graphene to realize the full reduce of this boric acid or boron in the seawater. And then we have also figured out the different positions that the nitrogen can be embedded into this structure. So there are in total 9 possible complexes. And we can see that one of them, as we highlight at this left corner over here, has 1 quaternary nitrogen atom and 2 adjacent hydroxy groups that will have the highest sort of energy, and that will have the most attractive force towards the boric acid. So our approach have the boron rejection of NGO at 5 milligram per gram boron concentration as high as 91%, and the boron absorption capacity of NGO is 23 times higher than pristine GO. And then the boron absorption capacity in the structure can be as high as 58 0.7 milligram per gram. And we have also been working on recycle for antimony to this nitrogen doped graphene oxide, and the antimony structure post absorbance have been utilized as sodium ion battery electrode. I think there are many things we can do to this new generation low dimensional nanostructure as effective low ion concentration water treatment. And then they may find interesting application in the future, for example, for some pharmaceutical wastewater processing, and then precious metal recovery like lithium, agriculture, and drug delivery, and so on and so forth. So I think we can contribute a lot to the society in terms of carbon neutral, and then also sort of our sustainability for the future smart cities or smart nations. And then we are looking forward to work with the expert here to further develop our technology and contribute more to the entire Asia and Asia Pacific regions. Thank you.
Thank you very much, Professor Ying. It was a very nice presentation. You introduced state-of-the-art nanomaterial, and thank you again. Are there any questions?
I have a question.
Yes,
Professor,
Professor.
this is Yong-Sul Song from NAEK. Thank you for your nice presentation. Very interesting.
Thank you, Professor.
Yeah, I want to know which is the most important properties of carbon nanomaterials for CDI systems.
Thank you for your questions. So there are like many sort of factors that can determine the effectiveness for this CDI, a carbon-based CDI. And for example, the high electrical conductivity, so the material must be very conductive, and a large surface area, so you may need to make a lot of pores. So the porous structure will be very favorable. So because the ions can be embedded into the porous structure, and also the pore size distribution, you don't want to make all the pores very big or very small, and the like a well-defined pore distribution, and also good wettability, so the water can easily go through the structure, and also sufficient ion diffusion pathways, so the ions can swim inside the structure. So those are the key factors to define the effectiveness of your electrode.
Okay, thank you.
Thank you, Prof. Song. Thank you.
Yeah. Are there any other questions?
I also have a question. It was a wonderful talk.
Thank you, Prof. Park. Yeah.
In particular, the use of the nitrogen doped graphene oxide or just the graphene oxide for boric acid removal,
yeah,
or boron removal from water.
Yeah.
As I understand, you are using the charge-based absorption.
Yes.
So electroadsorption. But
yes.
Is there any how can you guarantee the selectivity towards the boron material
Okay.
in the water if there are other negatively charged materials?
Okay, thank you. This is a very good question, because boron actually exists in water in the boric acid format. You can see over here, the boron is in the center, and we have 4 OH group at the each corner. So the whole structure is a negative charged structure. It's not like other metal ions, for example, sodium, potassium, calcium, magnesium, and so on. Those ions are like positive charged composite, and this particular boric acid is actually negative charged composite. And when this sort of composite being closer to this nitrogen doped graphene oxide, this nitrogen doped graphene oxide is actually positive. So in a way that positive will attract the negative composite, but then will expel this positive sort of composite. So the other metal ions will be pushed away. So this boric acid will move closer to the structure. After it moves closer to the structure, we can see over here, there will be a chemical reaction. One water will be reduced from over here. So that will generate B to O and then to nitrogen doped graphene oxide bond. So when the chemical bond has been generated, this boric acid will be permanently bound to the structure, become part of the structure, so we will be very stable. So in this way, we can 100% make sure that only boric acid will be attracted and attached to this structure, no other metal ions. Thank you.
Thank you.
Thank you.
Thank you for the question and answer. Before we move on to the next speakers, let me bring your attention to a couple of messages in the chatting window. One was, there was a request for the copy of the presentation files. That will be resolved by the members of NEK and the ASEAN side. And there is also a request to the AAET participants. If you can change your name with your appreciation, that will be great. We can identify the participants. Now let's move on to the next speaker. Is Professor Hyung-Kyu Park. He's a professor in mechanical engineering at POSTECH, Korea. His presentation topic is on understanding of nanoscale water transport phenomena for more energy efficient membrane technology. Professor Park.
Thank you, Professor Park. So in the interest of time management, I made a 21-minute long video out of my talk, so please enjoy.
Can everybody hear the sound? No. Right?
No.
Yeah, Professor Park, we don't, no sound.
Can you turn on your microphone?
No sound.
Hello, everyone. My name is Professor Hyung-Kyu Park. I'm a director of a Center for Low-Dimensional Transport Physics and a head of a laboratory of nanoscience for energy technology and sustainability in the Department of Mechanical Engineering of Pohang University of Science and Technology, POSTECH. Thank you very much for inviting me. Fast mass transport inside and across nanoscale graphitic surfaces such as carbon nanotubes and graphene, respectively, forms the basis of carbon nanofluidic phenomena and poses potential applications in energy and clean technologies. This talk will review the existing paradigm of the fast transport in carbon nanotube conduits, followed by our story of shifting the paradigm to a recognition that having a nearly frictionless channel could be equivalent to having no channel but only openings. Synthesis, concept of atomically thin porous membrane. Transport physics across the 2D pores points to an ultimate permeation of fluids in both molecular and viscous transport regimes, which envisions emergence of a high permeation membrane. The high permeation membrane is in need of proper applications, for which this talk is organized. Here we go. Membrane technology has been finding many attractive applications, including chemical separations, water purification, energy harvesting, and household and medical devices. By substituting a host of industrial processes, membrane technology poses great potential for the process intensification towards sustainable industrialization. For example, for energy savings point of view, they say membrane technology can help cutting costs for chemical separation industry. Chemical separations account for about half of the US industrial energy use, and it is the thermal processes that take up 80% of the energy consumption for chemical separations. Developing alternatives that do not use heat could make these separations 10 times more energy efficient. However, membrane technology faces its own problem of so-called a trade-off relationship between how well it separates chemical species and how easily it produces the products. This trade-off forms a certain maximum performance line called upper bound. Upper bound is not a thermodynamic limit. It is about technological state of the art. Every few years, it shifts upward little by little. For example, most of the polymeric membranes' performance fall below the polymer upper bound. Rising inorganic materials like zeolite, graphene oxide, and metal organic framework could overcome this upper bound by boosting the selectivity, but at the expense of permeance. They seem to make their own upper bound line in the performance chart. In order to overcome the upper bound limit, we need to come up with innovative ideas. To take a fresh start, I came to the very basic and looked up a dictionary for the definition of membrane. I could find biology definition and chemistry definition that share some keywords in common. A membrane is a thin layer permeable to a certain substances selectively. Conceptually, an ideal membrane is a 2D material that divides space into mixture and demixture by separation mechanisms. And we must understand that this separation process is not free. It needs to pay tax to the nature. What it means is that it generates entropy or dissipates energy. Otherwise, we're talking about Maxwell's demon here. The energy dissipation occurs near the membrane surface and inside the core. The dissipation at the membrane surface is partly inevitable if we want to separate chemical species. Hello everyone, my name is... But we can do something about the transport-related dissipation. This dissipation is primarily caused by a friction mechanism. In theory, we may decouple the friction-related dissipation from the separation-related dissipation and get rid of the latter to obtain the energy efficiency in chemical separation. Or we could also thin down the membrane to decrease the portion of the friction-related energy dissipation. And at the limit of this strategy, we come to a thinnest feasible membrane that the nature allows, an atomically thin membrane. By engineering the membrane in this way, we want to obtain a technologically good membrane that satisfies high selectivity, large permeance, and great in-operando stability. First, I will share with you a story of existing paradigm on energy-efficient transport through carbon nanotubes, and then I will shift the paradigm by enabling an atomically thin membrane capacitated with graphene. Here we go with the fast mass transport through carbon nanotubes based on a paradigm of minimizing the friction of transport. The pioneers of carbon nanofluidics had a mindset that the carbon nanotube interior could mimic biological transmembrane channels for water and ions. It is known that water molecules can spontaneously fill in the carbon nanotube interiors by adjusting their hydrogen bonding network. When the carbon nanotube diameter shrinks to sub-nanometers, in particular, they can even configure themselves into a single file with gaining additional degree of freedom. Transport speed of this configuration exceeds diffusion-like transport of man-made synthetic polymer membranes, and it is often comparable to those of biochannels. In words of water or liquid purification technology, the inner diameters of carbon nanotubes could potentially address reverse osmosis, nanofiltration, and ultrafiltration. Today, researchers understand the fast transport of water molecules confined in carbon nanotubes by both of their interesting hydrogen bonding network configuration and their relatively weak interaction with the smooth hydrophobic wall. For 1 nanometers-ish carbon nanotube channels, it is the traits of water molecules that run along in parallel, whereas for large carbon nanotube channels, it is the water nanotubes right at the interface of water and the graphitic wall that carry the bulk water confined within them to result in plug flow like velocity profiles. However, When it comes to a question, how fast is fast, data from both simulations and experiments are not entirely aligned. Perhaps the best way to resolve this conundrum would be to establish an experimental data for various carbon nanotube diameters. Unfortunately, counting water molecules is technically impossible at the moment. An idea to bypass this technological difficulty is to make a manifold membrane and obtain water transport rates in an ensemble averaged way. To this end, narrowing down the carbon nanotube diameter distribution within the membrane is significant. If we have 1 nanometer wide channels here and 5 nanometers there, the data would be close to garbage. My group has put efforts to synthesize vertically aligned carbon nanotube arrays of various diameters, each with narrow distribution. Early days, we varied the catalyst size. Later, we engineered the catalyst support layer of alumina in a way of preventing subsurface diffusion and the ripening of metal catalyst nanoparticles, resulting in a single-walled carbon nanotube forest with very small diameters. So we thickened each carbon nanotube via atomic layer deposition-based conformal coating and successively obtained membranes out of single-wall carbon nanotube arrays. Obtained water permeation rate was orders of magnitude enhanced in comparison to the Hagen-Poiseuille flow prediction. The slip flow theory could explain this result, which I believe is true, but this theory itself may not explain why the enhancement is only hundreds or thousands instead of a million or larger than that. This question is related to the conundrum of our field. Fortunately, there are 2 data points sharing the similar CNT diameters. One is my old data from 6.5 nanometer wide short double-walled carbon nanotubes, whereas the other from long multi-walled carbon nanotubes. My student and I speculated that the length plays a role in this diagram and replotted the flow enhancement factor with respect to the length over diameter. Then it appears that most of the published data from both experiment and the simulations collapse on a monotonic line in this new diagram, and the exponent in the log-log plot was close to a unity. If enhancement factor is linearly proportional to the aspect ratio of carbon nanotubes, it must come from the reference formalism to which we compare the water transport rate. By canceling out the aspect ratio L over D from both sides of this equation, we obtain a new scale for the transport rate of water flow rate through carbon nanotubes, the volume flow rate of water through carbon nanotubes. This volume flow rate of water through the carbon nanotube is proportional to the cube of the channel diameter and independent of the channel length. This observation hints that having such a slippery channel as carbon nanotube as the transport path is just like having no channel at all from the energy dissipation point of view. Imaginably, the carbon nanotube membrane permeates water just as a zero thickness orifice does. Then an analytical theory for the zero thickness orifice exists in the name of Sampson's formula, obtained by solving a linearized Navier-Stokes equation for an orifice having mathematically zero thickness. We assume that the transport rate through carbon nanotube channels relies on the entrance and exit resistance, which is shown here, but not on the channel resistance, and set then the maximum enhancement factor by substituting Q by with Sampson's formula to result in the maximum value of the enhancement factor. The result is striking. Most of the simulation and experimental data are gathering around the maximum enhancement factor line. In this diagram, the orange maximum line divides the domain into an unattainable region, a maximum transport efficiency region, and thermodynamically attainable region that the transport rate can sit in if the nanotube quality is imperfect and the flow resistance from the nanotubes takes part in the overall dynamics. Our experimental data lies in the region right below the maximum enhancement factor line, and gathering the later published data supports our understanding too. So, carbon nanotubes can provide very efficient transport pathways under nanometer scale confinement. By doing so, they pose a great number of energy efficient applications. In this paradigm, though, transport is limited to a material property. Manufacturing options have to be compatible with the selected material, which somehow limits rapid spread of this wonderful science into technology. In one way, this technological hurdle could be overcome by embodying the imaginable membrane, a membrane full of orifices of trivial thicknesses. 2D materials can enable this proposal. Unlike diffusivity tailoring, the thickness tailoring may free us from the material dependency. Here, the demand is the mechanical strength. But if the confinement length shrinks to vanity, the entire Fickian dynamics diverges to infinity. What can we expect at the zero thickness limit? The transport across 2D pores is featured with an absence of walls that confine transmitting molecules. Interaction of this confinement with gas molecules is characterized by collision, accommodation such as adsorption and desorption, and surface diffusion, whereas interaction with liquid molecules by long range of interaction, energy landscape, and friction. In the absence of these interactions, theoretical predictions are based on gas kinetic theory or Graham effusion for free molecular transport regime, and low Reynolds number orifice theory or Sampson's flow for viscous flow regime. What is still missing here is the kinetic theory of liquids applicable to the free molecular transport regime, and the chemical kinetic theory when the interaction between transmitting molecule and the aperture edge turns important. So the task is to manufacture a 2D membrane with precisely defined pores, obtain the transport data, and compare them with the transport theory previously explained. Our material of choice is graphene. Thanks to its sturdy mechanical property and molecular barrier property that implies molecular transport must take place through an artificial pore, we will perforate it on graphene. We have successfully placed 2 graphene layers on a 150 nanometer thick freestanding silicon nitride layer that has 64 of 5 micrometer wide holes. On the freestanding membrane, we drill the holes by use of focused ion beam milling. Thanks to the 2D nature of the target material, the drilling mechanism is rather simple. Let me show you here. If bombardment energetic ions happen to hit a carbon atom, the carbon atom gains a part of the kinetic energy. And once the energy gains overcome the lattice binding energy, the carbon atom can escape via 2D lattice. But if ions somehow miss carbon atoms on the left, the ions can just penetrate graphene without stripping off any atom. This simple mechanism may explain why sputter yield for the perforation process can be very small. Anyway, in this mechanism, focused ion beam milling can perforate pores one by one on a freestanding graphene layer. You might worry about the long process time of perforation, but we could drill a few million pores within a few hours. Although focused ion beam cannot warrant scaling up of the graphene perforation process, one of the clear advantages of this method is that one can end up perforating a wide variety of pore sizes. Indeed, we could drill on graphene pore sizes of 5 nanometers, 8 nanometers, 15 nanometers, 50 nanometers, 100 nanometers, etc., all the way up to 1 micrometers. The wide range of perforation capability has enabled us to explore the transport regime from free molecular to continuum viscous flows. At room temperature on 1 bar, nitrogen gas's mean free path is approximately 70 nanometers. Pores on graphene smaller than 70 nanometers shows the transport characteristic of Graham's diffusion clearly, and pores much larger than 70 nanometers present asymptotic behavior nearing Sampson's flow. And in between the two regimes, our experiment provides diamond data for gas permeation in the transition regime. What about liquid transport across two-dimensional orifice? Because of capillarity, liquid water did not cross over the graphene membrane if one side is wet. Once we wet both sides of the graphene membrane, water permeation is observed even at a small fraction of a bar of pressure difference. For a pore size range over 6 nanometers, we verify that Sampson's formula works well with predicting the liquid flux. For pores smaller than 6 nanometers, on the other hand, Professor Aluru's simulation has predicted a deviation from Sampsonian dynamics as pore sizes approaches 1 nanometers especially. A race has just begun to verify that prediction, with resulting in ambiguous experimental data for now, showing a large error bar and a pro-Sampsonian result. Transport at such small single-digit nanometer wide pores is not well understood theoretically, which is identified as an additional knowledge gap. The research field of the transport across 2D orifice pores is at its adolescence. The field is gradually growing in the field of engineering science, calling for scientists' further attention. Here is a brief discussion on the emerging high permeation membrane out of graphene, porous graphene. Figure of merit indicates that, thanks to ultimate gas permeation, the high permeation membrane will lie beyond the upper bound of current membrane materials. For ultrafiltration application, liquid permeation of the high permeation membrane exceeds that of polymer membranes, but just marginally. Surpassing PTFE-based membranes in water vapor transmission rate by many orders of magnitude, the high permeation membrane shows a potential for breathable fabric and the breathable membrane. Identified challenges to consider in further developments include addition of suitable separation mechanisms compatible with the high permeation membrane material, finding of methods for scaling up the membrane manufacturing, sustaining inoperando mechanical conditions, and assessment of concentration polarization and temperature polarization, to list a few. For overcoming the manufacturing hurdle and moving beyond the focused ion beam method, we have recently developed both top-down and bottom-up manufacturing methods of producing porous graphene membranes having pore sizes of few tens of nanometers. Efforts for understanding the zero-dimensionally confined transport physics and to find out engineering applications of the high permeation membrane have just begun. To this end, out-of-box thinking is needed. Thank you for your attention.
Thank you very much, Professor Park. It was a very nice video and a wonderful presentation. Due to the time limit, we can entertain one question. Is there any question? So, Professor Park, you briefly talked about the scale-up and the practical application of your findings. And so, is there any industries that started this already or still lab level? Can you briefly introduce that statement?
Thank you for the very technically interesting question, or important question. It's mostly in the lab, and a lot of labs all around the world are trying their best either to make a very, very small pores close to the molecular size. That's one direction of research. And another one is to make use of a tens of a nanometer pore size and then try to obtain the scaled up version. And some companies in, for example, one small medium enterprise in Switzerland is trying to increase its capacity of making porous graphene material for the breathable fabric application because the Gore-Tex patent is now free now. Other than that, I do not know exactly. One company, the American the airplane manufacturer, I just forgot. It's
Wing rocket.
no, it's the F-35 manufacturer. Anyway, that company has patented the design patent, but they did not make the product yet. So I would say the technological or industrial the production of a porous graphene material for membrane application, especially for water treatment, is at its very early stage. But many people are working on it.
Yeah, thank you very much, Professor Park. It was a very nice presentation on both science and engineering. Thank you.
Thank you.
Now let's move on to our last speaker, is Professor Chantarapon Palakonkule. She's a professor in chemical engineering at King Mongkut University of Technology, North Bangkok, Thailand. She will give us a talk on efficient removal of tannins from anaerobically treated foamy by forming protein tannin complexes followed by precipitation electrocoagulation.
Good afternoon, everyone. My name is Chan Palakonkul from King Mongkut University of Technology, North Bangkok, located in Bangkok, Thailand. I'm sorry I couldn't turn on my camera. It didn't work. I would like to thank everyone here from Korea and ASEAN countries for organizing this event. Let me share my presentation slide. Can you see it?
Yes, we can see.
Yes, we can.
Yes.
Okay, today I would like to share a research project I'm doing on wastewater valorization. The research project involves the recovery of tannins from anaerobic treated palm oil milk effluent using protein tannin complex, followed by precipitation and electrocoagulation. And here's the outline of my talk. In the introduction, I will introduce a current challenge for managing anaerobic treated palm oil milk effluent, and then propose the model called biogas tannin water model, which is an extended approach to a circular economy in palm oil milling process, and then introduce bud protein from slaughterhouse as organic coagulant of tannins, and then electrocoagulation and a key factor to achieve high removal efficiency, and then research strategy, methods, results, and conclusion. The palm oil industry is economically important in several countries in Southeast Asia, including Malaysia and Thailand. However, palm oil production produces large amounts of polluted wastewater known as palm oil milk effluent, or POME. POME is typically treated in anaerobic digesters to convert organic matter in the wastewater to methane. Anaerobic bacteria can degrade cellulose, hemicellulose, and other complex biopolymers, largely via extracellular enzymes. However, it is known that anaerobic bacteria can hardly digest phenolic compounds, including tannins, resulting in high color intensity of the treated effluent. Tannins are polyphenolic compounds that are two distinct types, hydrolyzable and condensed tannins. From our analysis, most tannin in pome are gallotannins, which is a type of hydrolyzable tannins. So we propose a new model for managing the pome. The model is termed biogas tannin water model. At the current, the industry treats the wastewater using anaerobic digestion, and the biogas produced is used for generating electricity and heat. The treated pome still contain residual COD of around 7,000 mg per liter and deposit on land. In this model, we propose to treat pome further, first to recover tannin. The tannins will be valuable products because gallotannins is known to have health benefits. It is an antioxidant, anti-inflammatory, sensory reinforcement, and anti-diabetic. Then after the removal of tannins, we will use electrocoagulation to remove other residual compounds, followed by softening unit to remove water hardness, and finally a membrane unit to improve the water quality for water recycling to the palm mill process. In tannin industry, tannins have been recognized for their ability to interact with proteins and form protein-tannin complexes. The formation of protein-tannin complex can lead to the precipitation of tannins and proteins. It depends on the chemical structure of tannins and proteins, protein charge, protein isoelectric point, and their concentrations, as well as environmental conditions such as pH and ionic strength. Over the past few years, tannins have been used for the removal of various proteins from beverage and animal food. In this project, we reverse the idea. We are going to use proteins for the removal of tannins in pome. What's the source of protein? We interested in waste from slaughterhouse because the waste has high volume, low cost, and contain high concentration of blood protein. In addition, the precipitation of protein-tannin complex is considered more environmental friendly than inorganic coagulation because no salt is added to the aqueous system, so no significant increase in water conductivity or change in water pH. For electrocoagulation, it has been demonstrated in the past few years to be an effective method for treating pome and other wastewater containing phenolic compounds. Or for the electrocoagulation, electrical current applied to the anodic electrodes, such as aluminum or iron or their alloys. The anodes are oxidized to release free metallic ions, which then combine to the hydroxyl ions generated at the cathodes to form metal hydroxides, polyhydroxides, and polyhydroxyl metallic compounds. The efficiency of the removal of tannins and other phenolic compounds can be as high as 80%, but the electrocoagulation requires high energy, possibly because high solubility of tannins in the water. In this table, show the literature data, we can see that electrocoagulation will have high COD removal efficiency when the target compound has low water solubility, or the target compound can react with the metal ions to form insoluble compounds. Otherwise, the removal efficiency will be very low. So, in this in this study, in the first step, we're going to perform the precipitation of tannins in the polymer treated effluent by adding pig blood proteins to reduce the solubility of tannins by forming protein-tannin complexes, followed by the separation of insoluble protein-tannin complex by centrifugation in step 2, and the electrocoagulation of the remaining soluble protein-tannin complex in step 3. For the coagulation study, we study the effects of protein type, pig blood, and casein protein, aqueous pH, and protein-tannin ratio on the tannin removal efficiency. And for the electrocoagulation, the electrode type, current density, inter-electrode distance, and electrolysis time will be optimized to minimize the energy consumption. For the results, first of all, we illustrate that the type of protein is matter. This figure compares the effectiveness of pig blood and casein proteins in removing tannins from the treated polymer. The investigation was performed with varying protein-tannin ratios between 0.2 to 1 by weight at an initial pH of 5. When using the pig blood protein, the tannin removal was highest at 62 to 64% with protein-tannin ratio between 0.2 and 0.33. The tannin removal was much lower when using the casein protein, ranging between 10%. And the type of protein has a profound effect on the removal efficiency of tannins, because the formation of protein-tannin complex depends on the interactions between the functional groups of tannins and proteins. So in the table, we can see that the amino acid composition of the pig blood and casein proteins are different. The major amino acids in the pig blood include aspartic acid, leucine, tyrosine. Thus, the major amino acid in casein include lysine, valine, and arginine. And because the experimental pH is at 4, which was lower than the pKa2 of aspartic acid, the amine group of aspartic acid will be positively charged and can interact with the carboxyl group on the phenolic rings of tannins via ionic bonds. In addition, the proton acceptor of the carbonyl amine and amine groups of aspartic acid could interact with the hydroxyl groups on the phenol rings of tannins via hydrogen bond. Similarly, at the optimal pH for the removal of tannins by casein protein, the amine group of lysine and valine can have positively charged. However, the difference between the pig blood and casein could be due to the proportion of amino acids that can interact with tannin to form the protein-tannin complexes. That is, the proportion of aspartic acid in pig blood was about 5 to 10-fold more than the proportion of lysine, valine, and arginine in casein. So when using the pig blood protein, the tannin removal was highest at about 60%, 65%, at the protein ratio between 0.2 to 0.3. When it's increasing the protein ratios further, the tannin removal decreases. The protein-tannin ratio has a profound effect on the removal efficiency of tannins, because when the concentration of tannin is too high compared to the when the protein concentration is too high compared to the tannin molecules dissociate from the tannin protein complex and redissolve. The figure shows tannin removal as a function of pH between 2 and 9. This figure shows the tannin removal as a function of initial pH between 2 and 9. The increase in pH from 2 to 4 caused the tannin removal to increase from 50 to 72%. Whereas the further increase in the pH reduced the tannin removal. The pH 4 was optimal for tannin removal via the formation of tannin protein complexes because of the relative strong interaction between tannins and protein at this pH. An increase in pH in the pH above 5 caused the dissociation of the complex, whereas the pH above 8.6 caused the hydrolysis of gallotannins. After separating the insoluble protein tannin complex by centrifugation, the suspension was subject to electrocoagulation to remove the remaining tannins. This figure shows the removal efficiency of tannins using electrocoagulation with aluminum and ion electrodes at an initial pH between 2 to 9, electrolysis time of 30 minutes and current density of 20 milliamp per square centimeter. When using aluminum electrode, the tannin removal reached 89%. The tannin removal was significantly higher for the electrocoagulation with the addition of without the addition of protein in the picture below. When using ion electrode, the tannin removal reached 72%. Similarly, the tannin removal was significantly higher for the system with the addition of protein. Electrocoagulation with aluminum electrode result in higher tannin removal than ion electrode because the formation of protein tannin complex is favored at acidic pH, whereas the formation of iron hydroxide complex is favored at alkali pH. In addition, aluminum hydroxide complex exists in various forms with more definite binding sites when compared to iron hydroxide complex. We found that the addition of protein helped increase tannin removal because the efficiency of electrocoagulation depends on the solubility of the target molecules. Once the blood protein was added to the system, the solubility of tannins was reduced due to the formation of the protein tannin complex. This figure shows the energy consumption as a function of the current density and electrolysis time. The system with the addition of blood proteins requires less energy to remove tannins because the shorter electrolysis time and lower current density. For the system with the addition of blood protein, a tannin removal of around 80% can be achieved with an electrolysis time of 10 minutes and current density of 30 milliamp per square centimeter, consuming about 12.5 kilowatt hour per cubic meter. Without the addition of blood protein, a tannin removal was 72% with an electrolysis time of 10 minutes, current density of 40 milliamp per square centimeter, consuming 25 kilowatt hour per cubic meter. The inter-electrode distance was reduced from 50 millimeter to 10, 8, and 6 millimeter to reduce the energy input. A decrease in the inter-electrode distance to 10 millimeter increased the tannin removal efficiency and reduced the energy consumption to about 6. Decreased the energy consumption from 12.5 to 6.3 kilowatt hour per cubic meter. And as the inter-electrode distance decreased further to 6 millimeter, the tannin removal efficiency decreased to 82%, with a slight decrease in the energy consumption to 5.6 kilowatt hour per cubic meter. By changing the electrode configuration from one pair electrode to monopolar series and 8-minute electrolysis time, we can reduce the energy consumption further to 2.4 kilowatt hour per cubic meter. This table shows the property of the effluent after the treatment by the precipitation and electrocoagulation using the optimum condition of pH 5, current density of 30 milliamp per square meter, and inter-electrode distance of 10 millimeter. After tannin precipitation in series with the electrocoagulation, the COD decreased from above 20,000 milligram per liter to about 700 milligram per liter with the addition of blood protein. And the cover lagoon appear dark brown color with a color value about 20,000 platinum cobalt unit, and tannin concentration about 545 milligram per liter. After the treatment, the treated polymer appear light yellow with a color value of about 700 platinum cobalt unit and tannin concentration of 36 milligram per liter. However, the total hardness still high, and we need to manage it further. These figures show the microscopic image of the frogs. The frogs from the system with the addition of blood protein were the largest and densest at the optimum electrolysis time of 10 minutes, at which the tannin removal efficiency was the highest. In contrast, the frogs from the system without the addition of blood protein were smaller and less dense. From the same image, the frogs consist of small aggregates that were densely interconnected.
So can you wrap it up in, couple of minutes?
Yes, and in the conclusion, blood protein caused the formation and precipitation of insoluble protein tannin complexes. Subsequent electrocoagulation caused the precipitation of soluble protein tannin complex. Type of protein is matter. Pig blood protein contains aspartic acids as the major amino acid composition. So at the working pH, the amine group is positively charged and can interact with the carboxyl group of the phenolic rings of tannins via ionic bonds. At an optimal pH with pig blood protein, the tannin removal reach 93%, COD removal 96%, tannin removal of 93%, COD removal 96%, and color removal of 97%. However, water recycling is not yet possible because the total hardness of treated effluent still does not meet the requirement. In future, we are aiming to find solutions to reduce the hardness further. Okay, thank you for your kind attention. That's the end of my presentation.
Thank you very much, Professor. Yeah, it was very practical and a very good idea. Due to the time limit, we can entertain one question. Is there any question? Okay. So, the professor, may I ask one question?
Yes.
Yes, the idea is very interesting. So, if you want to use this practically, so the idea is you transport pig blood to Komi wastewater treatment plant, or how will it work in large scale?
In large,
yeah, practically.
okay, yes, in large scale, we need to transport the pig bat to the palm mill industry and do the coagulation there. But since the amount need to for the coagulation just depends on the amount of tannins in the wastewater, so it will not a big volume.
Oh, I see. It won't be a huge volume.
Yeah.
Okay. Thank you very much. Okay,
Thank you.
Yeah. Now, let's move on to the panel discussion. Today, we have 4 experts from Korea and ASEAN on our panel. We have 4, so let's start one by one. I give 5 minutes to each panel, and during the 5 minutes, each panel can speak on their own ideas or comment on the presentation. Our first panel is Professor Jae-Young Yoon. He is from the Department of Chemical and Biological Engineering at Seoul National University. He is the former the chairman, president of the Korea Environment Institute. Professor Yoon, can I give you the mic to you?
Okay. Thank you for inviting me. This wonderful seminar. First of all, I'd like to congratulate first ASEAN-Korea Water Treatment Working Group Seminar. Right. Let's see. We have 4 great presentations. If I classify these 4 presentation, maybe 2 presentation is more like pioneering research work activity. In 2 presentation is more close to practical study to solving real life problem, right? Both of them is very interesting approach. Engineering is always closely related with the reality. We need to provide solutions to solve the problem. Then we do some basic research work. In that sense, we have classified 2 group of the presentation. And this seminar is organized by National Academy of Engineering of Korea, NAEC, and AAET is Asian Academy of Engineering and Technology. It's not professional society. Many of them belong to professional society in the very specified research area. Is water treatment or membrane technology, or is that renewable energy technology development. I think that seminar we are handling in this level of umbrella has to be formulate direction. Why we gonna do this one is rather than dealing with very professional society. That's the one thing we need to think about further. Then Korea and ASEAN is geographically very close, right? Close. And Asian country I guess 10 countries belong to ASEAN. Many of them, almost all of them, is growing economy, is large populations. Then Korea is a relatively recently developed country. Then experience and expertise may be shared together for mutual beneficiaries, right? Then what is the mutual beneficial area we can work together? We need to formulate in that one. Then what is the common challenging we are faced in water area or energy area? At the time when I was president in Korea Environmental Institute, 99 to 21, Korean government announced carbon neutrality by 2050. It's a little bit surprising announcement, even for me. Korea is now heading for carbon neutrality. By 2050, 2030, we have to reduce 40% of greenhouse gas emissions. It's really challenging task. We are transforming society in every sector of our society. Then international collaboration becomes much more important. In 40% of reduction of greenhouse gas emissions is 40 million tons of greenhouse gas will be from international collaborations. So international collaboration with Asian country will be becoming much more important. Then how are we going to do that? Right. In here is academic. I think most of them, you are academic people, but Asian we have to collaboration expand more. Is public officials or industrial sector, right? It's professor cannot do much of that in terms of those activities. Professor maybe do good research work, publish good paper, maybe to transfer some of the knowledge, right? Then we needed to establish some kinds of some solid platform. That could be seminars, that could be conference, right? That Professor Park Jae-woo maybe think about more later. And capacity building also one of the approach we can do further. Once we have something we can communicate or transfer, we can develop some training program, technical skill or knowledge. Then what kinds of knowledge we need to transfer? Not quite sure at this moment. We need to find out those things. And then further, we can develop joint research program, or R&D program. I don't know, is ODA program, green ODA program. We can develop such a program. That's I have opinions in this as this discussion. And Professor Park, hello. It's Park Kyung-gyu. How are you over there? Perfect. I met him long time ago in Switzerland.
How are you, sir?
He came back. He did very much pioneering research work in membrane technology, nanoscale. Right? Congratulations. It's your further progress. And I enjoyed Professor Wing's work, right? Because I did a similar research area, CDI, BDI. We have a conference in early part of the June in Taipei. Professor Chia Hong Ho is organizing. So you may have interest in the conference. And also is YJ Kim, his research work that's the very important technology, small scale hydroelectric power generations is in the era of carbon neutral society, renewable energy, and is that Chanta Rapono professor. I enjoyed your work. Yeah, is tannin. I realized tannin wastewater is very important problem in Thailand. Right. I wish you have further progress in that area. Thank you very much. Bye.
Thank you, Professor Yoon. Yeah, it was very nice comment. Especially Professor Yoon reminded us of the importance of our direction or our mission of this working group. So we will keep that in mind and we're working forward for the further development. Thank you very much. So the next panelist is Professor Junhong Park. He's a professor in civil and environmental engineering at Yonsei University. He is currently the president of the Korean Society of Water Environment. Professor Park? You need to turn on the mic, Professor Park. Yeah.
Yeah, first of all, thank you very much for your invitation. Also, the Professor Jae Park, you organized a very wonderful session. The topic is very relevant, water and energy. And also the selection of the topics are it's two topics about the low energy water treatment, new technology. And Tannin talk, I think that's kind of circular economy technology, I think. And then the hydropower is very relevant issue about the water energy nexus issue. So I enjoyed this very diverse and interdisciplinary selection of the talks. Thank you very much for your hard work, Dr. Park. Regarding the first talk, I'm interested in that hydropower, especially in Korea, because we have to increase usage of renewable energy. As you know that the supply of electricity by renewable energy, such as the sunlight energy and the wind energy, they are not that stable in terms of the supplying electricity. So then we need kind of regulator. But as you know that fossil fuel power plant and then the nuclear power plant, it's very difficult to turn on, stop and turn on again. It takes a while. So it's not that useful to regulate the unbalanced supply and the demand between by the renewable energy. However, the hydropower is easily turn on and produce the electricity immediately. So if the demand, the energy demand and the electric supply are not balanced, the hydropower can be regulated that gap easily. So that is important to the role of the hydropower. But the percentage, the current contribution of the hydropower in Korea is so low. I think we have to increase the contribution of hydropower. Unfortunately, big dam hydropower has so many environmental impacts. So that's why I think the Professor Kim suggests a small hydropower. I think that's very reasonable and wise way. So Korea government should think about how to increase that contribution of the small hydropower. But same time, when we use small hydropower, then we have to worry about some kind of water quality and water ecology issue around that area. That should be carefully considered. Otherwise, that integrated water management would not be well done. So when we think about energy and carbon neutrality, same time, we have to be carefully think about water issues in that region. I think that we have to consider together in this workshop as well. That's my comment. Now is your mic.
Done. Okay, thank you very much, Professor Park. Yeah, you saved us some time. Yes, the importance of the energy and the relationship with water is very important. So you emphasize that to us. Thank you very much. So now let's hear from our Asian panelists. The first panelist from Asia is Professor Stephen Lim from Malaysia. He is currently serving as the chairperson of the Center for Photonics and Advanced Materials Research at University Tunku Abdul Rahman. Professor Lim?
Thanks, Professor Park, for your introductions. Yeah, first of all, I'd like again to thank all the speakers and all the panelists for contribute to our this first ASEAN-Korean water research seminars. So it's very interesting and delightful to hear all of your presentations. So as pointed out by Prof. Yoon Jae-yong, later our first panelist just now, yeah, this really our intentions for these seminars that we would like to have better research collaborations with the international partners. For example, I think even in my country, Malaysia, we do have a lot of researchers working on similar areas, whether it's on nanomaterials of membranes or even for the electrocoagulations to remove the polymer treatment. So this is also quite relevant in my countries. So we hope that through these collaborations and we can actually have researchers working together without having for them to actually repeat the same things, so that we can actually cooperate together and move forward. So that will be the main intention. Hopefully we can actually have a lot more fruitful international collaborations after these seminars. And also, of course, we also have second seminars later on scheduled somewhere in August. So that time we'll have more speakers to share their research to all of us. So hopefully again, all of you can attend that time. Okay, so back to our four speakers, four excellent speakers today. So just maybe have some brief summaries of what they are presenting. Our first speakers is Professor Kim, basically presented on the importance of the hydropowers. And in my country, Malaysia, for example, hydropower is actually a very important energy generation resources. So of course, one of the issues is that the large-scale hydropower systems is very costly, and if we can actually implement some research on a small-scale hydropower, it can really benefit power generations for rural areas, especially for those villages where they have difficulty access to electricity. So this might be something that further research can be looked into, how we can provide using small-scale hydropowers to provide electricity to those small villages in rural areas. Yep, so that is very important. And our second presenters, Prof. Yang, presented again very excellent presentations on the low-dimensional nanomaterials. And from her presentation, I actually learned quite a lot, especially on how we can use a variety of nanomaterials to perform water treatments, actually to remove, for example, using the capacitive deionization methods for the boron removals. So, and also the desalination battery, I think, is also quite interesting. We think that if we can't have some research on this part, we can actually generate a lot of energies based on the content or the salinization in the water, in the seawater especially. So I think there is also one thing that's the research area that's very interesting to me. And of course, the third presenters will be again the presentations by Prof. Park from PostTech. So again, on the he actually deals a lot with the fundamentals theories for the development of the mass transfer in the membrane separation systems. I think that is very useful, as well as in my university's Tungku Abdul Rahman as well. We have several colleagues, especially there are some are present here today, Dr. Chong, that they're also working on the membrane separations techniques. But of course, some of the technical difficulties that they're facing, I think, has been actually answered by Prof. Park as well. So I think we can actually think up. These are my colleagues that are working in the same areas together with Prof. Park, so that we can come out together with some research collaborations together, which I think Prof. Park can share a lot of your expertise and experience in the membrane development systems. So we look forward to actually have a really good breakthrough in the membrane technology development. Yeah, thanks, Prof. Park, for your presentations. Yep, and the last one, yeah, I'd like also to thank Prof. Chandrapon, who gave us a very interesting perspective on how we can't remove tannins from polymer. And as you all know, Malaysia, we also have a country, have a great abundance of palm oil trees, and we're also a great palm oil producer country. And polymer has always been one of the waste, a huge waste in our country as well. And also currently, I think most of our industry are using the anaerobic digestion, which I think can be further improved And Prof. Chandrapon actually presented a very sustainable and innovative solutions where they're actually using a bio-based waste, which is very environmental friendly. So I think this will be something that I myself also look forward to explore further with Prof. Chandrapon in the future. And also, I myself have been also studying a bit on the electrocoagulation system, and currently we have some research on using it to remove some heavy metals from the semiconductor industry. So from this expertise, I think again, there are actually a lot of opportunity that's our countries, ASEAN and Korean, we can actually work together. So I think this seminars actually achieve its aim where we can get to know each other better and find out the starting point for collaborations. Yeah. So I hope that each one of us will have a great deal of information and be able to later on push this information to a fruitful collaboration. Yeah, that's all for my comment. Yeah, thanks, Prof.
Thank you very much, Professor Lim. Professor Lim is one of the leaders of this working group. So he advertised the next seminar, which will be in August. So everyone should know that and should come back for the next seminar. Okay, finally, let's invite our last panelist from Myanmar, Dr. Ki Nin Tang. He is the initiator of Myanmar Water Think Tank, chair of the Water Mothers Organization of Myanmar, and Myanmar country chairman of Eco Civilization.
Thank you very much, Professor. My respectful greetings to all the professors and panelists and the audience. I am very grateful to join this panel and to talk a little bit about our thoughts from Myanmar points of view. May I please share my notes through the screen sharing? Actually, our last panelist and also our leader, Professor Lim from Malaysia, he actually ended with the sentence, "We are here to find out the talking point." It is this, I am going to start with his last sentence. I have tried to find out the relevance between the ASEAN-Korea Water Treatment Working Group, this very inaugural seminar. This is the first one, and the current status of Myanmar. Actually, I must confess, I was scared. I was scared to be on the working group. And I was very scared, how do we really collaborate within this seminar, because we do not have the membrane research, for example. In UNESCO IHE, where I studied, we have a friend who did the research, PhD research on membrane and the culture and so on. But she is from the different branch where I was studying the hydroinformatics. However, the hydroinformatics has plenty to do with the wastewater treatment, especially in our area of this sustainable development goals. We are very behind the other countries by any measures, and we have to recognize it first, and we have to understand how do we really leapfrog and get the benefit of the other advanced countries. So let me draw my thoughts back to the seminar. We have 4 very distinguished speakers, starting with Professor Kim, talking about the prospects for small hydropower development to support carbon neutrality policy. Actually, he said it all in that title, because he is saying that it is not the time to do the business as usual. Number 2, he is telling us that we have to think of the carbon neutrality whenever we plan the dams. And then he also explained about the policy. So I was very pleased. Okay, I get the fast relevance. I'm not going to go through all the detail because 3 panelists already have detailed, so I will not do it, just not to reinvent the wheel. The second one is about the nanoscale water transport phenomena towards energy efficient membrane technology. So I really go back to my 1990s knowledge of membrane technology, and I try to concentrate on his presentation. And what did I found out is the lesson. Oh my God, our young water professional, our youth has to go and study this advanced membrane technology. Otherwise, we will be very late, and we are already late. But don't cry over the spilled milk and how do we leapfrog. That was my thought after listening to this membrane technology. And I understand that also it is still possible if we have a young and bright men and women from Myanmar, we can send it to the, universities where this technology is. Then I feel a little bit relaxed. Okay, we only have to do the collaboration. And the third one is about the low dimensional nanomaterials. By the way, that membrane technology and also nanomaterials for water treatment, Professor Yang, these two also mention about the ocean and ocean pollution and how to make this much better way. So I realized that, okay, we have a crossing path in research because we are also tackling the ocean cleanliness and to reduce the ocean pollution. But I will not go into detail, but if we have the mutual interest, please call me or email me or through the AAET, through Malaysia, through Professor Lim, yeah, or of course our Professor Parker. Now, having said that, the last one is the Thai professor. She is talking about protein tannin complexes, followed by the precipitation, electrocoagulation. Actually, it is very interesting for me. And also, we are next door neighbors, and I was thinking maybe we can have the field trip to her laboratory and joined with our biotechnological students, and we can do this collaboration. Having said that, let me go all the way to Myanmar, hydropower considerations. I hope I can go to the next slide. Let me. Yeah, I got it. Sometimes my computer does not obey me. So when we think of the reform considerations, we need to reform our mindset. And that is my first goal as the chair of the Eco-Civilization Myanmar Wing, because I realize that all the projects are managed by human beings and all the research are conducted by human being, and we also go to other planet and it is human being. So the thing we have to think is, how do we decide upon which factor we decide, and what is the mindset we are taking, and which one we favor. Do we favor the money gain? Do we favor the green gain? Do we favor the sustainability of the planet? Or do we favor both the people and the nature? So now it's time to think of both people and nature together. equally. And that is my first statement. The second is, okay, this is for the universe. And now if we go to the tiny little country in the very dark corner called Myanmar, we need the institutional arrangements, but it has been very difficult from 2011-12 to 2021, because I myself was advising the vice president of Myanmar, the national vice president, in 2 consecutive governments, together with my fellow advisory group. We were 37, I was the secretary, I was the whip. I know from my own experience for 10 years, talking with 2 governments, but both of them are trying to reform. No government drop it, but it is not easy. Why? We are not only talking about the president, prime minister, minister, and so on. We are talking about the whole populace. Therefore, the multilateral governance come in the way. Multilateral government also speaks of, we have to speak with one word, same mind, common goal. And that is why if we change our mindset, our reform will be easier. Then we plan, of course, planning process is little bit relatively simple, but the third last point,
Dr. Tai? Apparently, she has some difficulty in connecting with us. Dr. Tai?
capacity is the one thing, participation is the another thing, the willingness.
Dr. Tai?
And prevailing, yeah?
We promised that we will finish 4:15. So
Yeah.
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 Can you wrap it up in a couple of minutes?
Of course, I will wrap up in 1 minute.
Thank you.
Is it okay? Yeah.
Yes.
So prevailing socio-economic situation, okay, and the political system. So these are the things we need as we are given as boundary conditions. So within that boundary conditions, we also have the natural favor, like how many precipitations we have. I'm not go to the numbers. So here you will see the catchment area and the surface water and the groundwater annually, okay? So annually we have this much amount of water. Why can't we be rich like Korea? No, because we don't do the reform. Korea did it. That is the difference. So on the basis of this, we have this much of groundwater, and also we have these particulars of land use. So land use is also very important for the water resources. And we have this much dams. You can see 2018 area, and we have more than 600 dams. And that is directly relevant to Professor Kim's dam aging. So we need to do the research on aging of the dams. And we have the basic data, and we have the energy mix, the basic scenario, and we also have the solar starting point. We have not much doing, but 100 houses. Then whatever we are behind, we have to also fulfill this 2030 agenda. So we are only picking the SDG 6, and we are starting the SDG 6 monitoring in Myanmar. So all the research partners are invited, and we would very much like to talk with you about the target 6.A and target 6.B. I will not go through the detail, but here what we did was in 2018 workshop. So it has to be going on, and my offer or my request or my appeal to these professors is we are actively seeking research partners. Thank you very much, sir.
Thank you very much, Professor Time. I'm sorry for not being able to give you full time, but
No problem.
yeah, thank you very much for your nice presentation. You made of your own presentation file. If you don't mind, please share the file with us later on, okay? So that the other people can take a look at your file more closely. Okay, so this is it for the day. Thank you for all your active participation. Now it's time to wrap up the first ASEAN-Korea Water Treatment Seminar. I hope you all had a meaningful time with us, and hopefully we'll be able to see you in August. Personally, I learned a lot, and I was very impressed with the quality of the presentations. I hope everyone also feels that way too. Thank you very much again. So see you in August. Thank you.